This is the default line, the line that sits inside almost every deep learning model on Earth. Image recognition, machine translation, the giant language models everyone talks about, and almost nobody who types it knows the truth. Adam isn't one idea. It's a stack of clever patches piled on top of an original idea from 2011, and by 2018, researchers discovered that even Adam is broken, in a very subtle way. Adam equals AdaGrad's dream, plus RMSProp's bug fix, plus momentum's inertia. Today we dissect every layer, and we find out where even the final layer still cracks. Let's dig back to the root. The eternal headache. Choosing a learning rate is a nightmare. Too big and training explodes. Too small and it crawls for a lifetime. Momentum, the last video, fixed the oscillation. But it still left us with one knob, alpha, shared by everything. Here's the real history. In 2011 came AdaGrad from John Ducci, Elad Hazan, and Yoram Singer, published in JMLR in 2011. It was born from the theory of online learning, not from neural networks. It became the star for sparse data, natural language, online advertising, where a handful of rare features carry enormous weight. Around 2012 came RMSProp from Geoffrey Hinton with Timon Tleeman. The dramatic detail. It was never published as a paper. It lives in Lecture 6E of Hinton's Coursera course, one of the most cited works in the field that isn't actually a paper. Also in 2012 came Ada Delta from Matthew Zeiler, discovered in parallel, with the same learn-to-forget instinct, and even bolder. It tries to remove the learning rate entirely. In 2014 and 2015 came Adam, from Diederik Kingma and Jimmy Baugh at ICLR 2015. The synthesis, momentum plus RMSProp plus one subtle correction trick. Then the 2018 twist, AMSgrad from Reddy, Kale, and Kumar, an ICLR 2018 best paper. They proved that Adam's own convergence proof was flawed, that Adam can fail to converge in certain cases. Even the champion is imperfect. To understand why Adam won, we have to walk the exact road it walked, starting with a beautiful idea that carried a fatal flaw. Let's build the whole metaphor with pictures first. Picture a ball rolling inside a narrow ravine, a long, thin taco shell. It's steep across the short axis and gently sloped along the long axis. With one shared stride length, you're trapped. Make the stride big enough to make progress along the valley, and the ball bounces off the two steep walls. Make it small enough to kill the bouncing, and it crawls down the length of the valley, slower than a snail. Now, you've seen this ravine before. In the last video, momentum tamed it by letting the sideways bounces cancel each other out while speed built up along the valley. Adaptive optimizers attack the very same picture from a completely different angle. They don't cancel the bounce. They shrink the stride on the bouncy axis in the first place and stretch it on the flat one, the aha. Stop using one stride for everything. Give each direction its own stride. Set by one thing: how big the gradients along that direction have been. A direction whose gradients are consistently large. The steep short axis automatically shortens its steps. A direction whose gradients stay tiny. The flat long axis confidently takes long ones. And notice the trigger is size, not shakiness. A wall that's smoothly steep, no bouncing at all, still gets a short stride, purely because its gradients are big. This whole family is built from two questions, not one. First, how long should we remember the roughness? That single question is what separates AdaGrad from RMSProp. Then Adam asks a second. Should we also remember which way we were already heading? Roughness in the denominator, inertia in the numerator. That's the entire stack. Let's bring back the base update everyone already knows from the last 3 videos. Theta is updated to theta minus alpha times g. Here, theta is the parameter, alpha is the learning rate, and g is the gradient. Now graft the adaptive idea onto one parameter. Shrink the stride by how much gradient this direction has piled up over time. AdaGrad does exactly that by accumulating squared gradients into a memory g that only ever grows. G becomes g plus g squared. Then theta is updated to theta minus alpha, divided by the square root of g plus epsilon, all times g. Write it like a sentence. Add this step's g squared to a running total g that never resets. Then the bigger that total has grown, the more gingerly I step. A direction that stayed smooth keeps g small and gets long strides. Epsilon is just a speck of dust, so we never divide by 0. Watch the very first step. G equals g squared, so the square root of g is approximately the absolute value of g. And the update is approximately alpha times the sine of g. A full learning rate step, the magnitude stripped away. And everything here is element-wise. G squared, the square root of g, and the division all happen per parameter. One private tube per direction. One private tube for each of billions of mismatched directions. That's AdaGrad's power, and it's real. But look at that clip again. The tube never drains. So as training runs long, every stride creeps towards 0, and the model freezes mid-descent. That flaw isn't about scale. It's about time, and it's the exact hole RMSProp was built to patch. Climb the ladder without skipping rungs. Start with one parameter, which we just did. Move to 2 parameters. That's exactly the ravine from before, now with the AdaGrad formula bolted on, then hyperspace. A real network has millions to billions of dimensions. Don't try to picture it, but the math is identical. Every dimension keeps its own memory, g for direction I, and gets its own break, alpha over the square root of that g. Note the single alpha never leaves. It's a shared base that each dimension divides down for itself. Now the anatomy of a real network. This is why one shared stride fails. Gradients in the first layer and the last layer can differ by orders of magnitude. 1, alpha can't be big enough for the quiet layer and small enough for the loud one at the same time. And sparse features, the embedding of a rare word, only receive a gradient once in a while. Here AdaGrad shines. Because that dimension's g barely grows, it keeps a long stride and learns fast the moment the rare word finally appears. This is AdaGrad's killer app, not its weakness. Watch that forest again. The exact rule that keeps the rare word bar tall is the same rule quietly shrinking every other bar towards 0. On the toy ravine that never bites. But let AdaGrad run long on a deep network and every bar eventually freezes. It strangles itself with its own memory. The trouble begins. Each problem here is a direct consequence of the large-scale setting we just built, and they stack. Solving the first 2 is exactly what creates the third. Problem 1. One learning rate doesn't fit all. 2 things collide. A narrow ravine means the loss falls steeply in some directions and gently in others, high curvature versus low. On top of that, the parameters themselves live on mismatched scales. Either way, one shared stride alpha is always too big for the steep directions or too small for the flat ones. Never write for both at once. Problem 2. Sparse features get starved. A rare but important direction fires only now and then. So under a single global rate, it barely moves across all of training. What it actually needs is a larger effective stride on the rare occasions it does fire. Give each parameter its own rate, scaled by its own gradient history, and this dissolves. This is exactly where AdaGrad was born to shine. So AdaGrad answers both of those in one stroke. Per parameter learning rates, each scaled by that parameter's own accumulated history. The fix works, but it carries its own poison. Problem 3. AdaGrad's fatal flaw. The break never releases. Its memory, g equals the sum of g squared, only grows, never shrinks. So the denominator, the square root of g, swells forever, the stride shrinks toward 0, and learning grinds to a crawl, sometimes long before the ball reaches the bottom. On a short, convex problem, that decay is fine. It's even provably optimal. On a deep network trained over hundreds of thousands of steps, it's death. Here's the counterintuitive gem. The very thing that makes AdaGrad wonderful, its infinite memory, the full sum that hands it convex guarantees and keeps sparse features alive, is the exact thing that kills it in deep learning. Same trait, two fates, decided entirely by context. The strength and the fatal flaw are one and the same. The whole problem fits in one word. AdaGrad cannot forget. So, what if we taught it to forget? Let's grow the family one formula at a time. And one thing to say out loud first. Every operation here is element-wise, one per parameter. The squaring, the square root, the division, all applied coordinate by coordinate. That is what makes each direction gets its own stride, literally true. Not a figure of speech. Start with the base you already know. Theta is updated to theta minus alpha times g. Step downhill, fixed stride, then AdaGrad adds the memory denominator. G becomes g plus g squared. Then theta is updated to theta minus alpha over the square root of g plus epsilon times g. Each direction tunes its own stride based on its entire history of gradient size. The weakness that forces the next step. G only ever grows, so it heads to infinity, and the break never releases. Then RMSProp swaps the running sum for a forgetting moving average, an exponentially weighted moving average. V becomes rho times V plus 1 minus rho times g squared. Then theta is updated to theta minus alpha over the square root of V plus epsilon times g. Remember only recent gradient size, typically with rho equal to 0.9. The square root of V is precisely the RMS, the typical magnitude of the recent gradient, which is where the name comes from. In the metaphor, the shock absorber is now responsive to the current terrain, no longer choked to death by the distant past, a parallel branch worth a brief mention. Ada delta. Same learn to forget spirit, but it goes further and drops alpha altogether, using the ratio of the RMS of the steps to the RMS of the gradients. An elegant fork, just less widely adopted, then atom, momentum plus RMSProp. It adds a first moment, inertia, alongside the second moment, the shock absorber. M becomes beta 1 times M, plus 1 minus beta 1 times g, that's the inertia. But note it's a running average of gradients, not the raw sum classical momentum kept. And v becomes beta 2 times v plus 1 minus beta 2 times g squared. That's the shock absorber, like RMSProp. So Adam has both the ball's inertia and a self-tuning stride for each direction. And here's the consequence 90% of tutorials skip. Bias correction. Because m and v are averages that both start at 0, the earliest steps are dragged towards 0. This isn't an optional trick, it's the price of using averages instead of raw sums. We fix it by dividing by 1 minus beta to the power t. So m hat equals m divided by 1 minus beta 1 to the power t. V hat equals v divided by 1 minus beta 2 to the power t. And then theta is updated to theta minus alpha times m hat over the square root of v hat plus epsilon. In the very first steps, we inflate the estimate to undo the pull towards 0 it was born with. The legendary defaults. Beta 1 equals 0.9, beta 2 equals 0.999, and epsilon equals 10 to the minus 8. It looks like Adam is the summit that closes the story. But it isn't the real default of today's world, and its proof still hides a crack. Reset the 3-question frame so you actively recognize the pattern. For every real training situation, ask yourself, 1. What does the loss, the error, measure here? 2. Which knobs are being tuned? 3. How big is the real scale? Now the tree of variance after Adam. Each fixes 1 point, Adam W, from Loshkolov and Hutter in 2017, and at ICLR 2019, pulls weight decay out of the adaptive step. Read it like a sentence. In plain Adam, the regularization term gets divided by the square root of v along with the gradient. So heavily updated weights secretly get less decay than you asked for. Adam W applies the decay straight to the weights instead. This is the true default for transformers and large language models today. And it loops right back to the hook. The line people actually type is Adam W Nadam from Dozat in 2016, Boltz Nesterov from the last video, onto Adam's first moment. Peek 1's step ahead, then commit the inertia. Only the m hat term changes. AdaGrad from Ready in 2018 replaces v hat with the running max of every v hat seen so far, so the shock absorber can never suddenly loosen. This is the direct patch for the convergence bug we dissect next, and an optional depth branch. Radom, from Liu and colleagues in 2020, rectifies the wild variance of the adaptive rate in the very first steps. The formal version of why we need warm-up, which is next. Now, practice, each tip reconnected to the shock absorber metaphor. Warm-up plus cosine decay. In the first steps, V is estimated from almost no data, so the shock absorbers twitch wildly. So start alpha tiny and ramp it up, letting the absorbers settle, then decay it smoothly toward the end. The role of epsilon. It isn't just about avoiding division by 0, it's a floor on the shock absorber. On a perfectly flat direction, where V hat approaches 0, the stride would blow up to alpha times m hat over epsilon. Epsilon is what caps that maximum stride so the hiker can't get flung. And gradient clipping chokes off exploding gradients before they reach the update, reconnecting to the scale mismatch from earlier. Now apply the 3-question frame to 2 flagship settings. First, training a large language model, the setting that deserves the most screen time. 1. The error is cross-entropy for predicting the next token. 2. What's tuned is billions of weights on wildly mismatched gradient scales. exactly where AdamW shines. 3. The scale is billions of parameters, thousands of GPUs, weeks of wall clock time. Second, computer vision with CNNs. 1. The error is misclassification. 2. What's tuned is the filter weights. 3. The scale is millions of images, but many groups here return to SGD plus momentum, which leads straight into what's next. That Adam line from the top of the video is really the third generation descendant of a 2011 idea. But why do computer vision researchers so often refuse it? In parts 5 and 6, we patched every kind of hole. The break that wouldn't release, the mismatched scales, the initialization bias. But some limits aren't bugs to be fixed. They're the inherent price of adapting. However smart Adam is, they remain. Adaptive methods can generalize worse than SGD. Wilson and Skolzig, in their 2017 NeurIPX paper, The Marginal Value of Adaptive Gradient Methods, showed that Adam often trains faster. But SGD plus momentum generalizes better on many vision problems. Reaching the training loss bottom fast is not the same as reaching the good bottom. And to distinguish this from part 5.3, this isn't learning halts early, it's learning finishes, but lands at a worse optimum for new data, an honest caveat. This gap is domain dependent. Later work narrowed it. AdamW's decoupled decay recovers much of the lost generalization. And in language models, the picture flips. Transformers effectively require adaptive methods. Plain SGD barely trains them at all. So the takeaway isn't SGD is better, it's that fast to a floor and lands on a good floor are two different prizes. Adam can fail to converge. In theory, Reddy, in 2018, showed that because V forgets. On certain problems, it can downweight a rare but large gradient, so it oscillates without converging. Here's the poetry we promised in part 0, the very forgetting of RMSProp. The trick that rescued AdaGrad from freezing is the same trick that breaks Adam's convergence. The fix, AMSGrads. Ratchets V with a max, so the break can never loosen again. But AMSGrad is rarely used at scale. The gap between a heuristic that works well and a clean theoretical guarantee is still there. No free lunch. The absorbers are bolted to the axes. Adapting means rebending the geometry per coordinate. So Adam's shock absorbers are bolted to the compass directions of the coordinate grid, not to the valley's true diagonal. If the real valley runs at 45 degrees, each absorber misreads its own axis and the hiker zigzags. Rotate the whole map and Adam traces a different path. Plain SGD would just trace the same path, rotated. Adam has quietly traded rotation invariance for per-axis adaptivity. And if the roughness estimate is wrong, it steps confidently in the wrong direction. The knobs don't disappear. They change shape. Adam doesn't remove alpha. It's still right there in learning rate equals 3e minus 4. What it buys you is a single alpha robust enough to reuse across problems without retuning. The price. It spawns beta 1, beta 2, epsilon, warm-up, and the question of how to attach weight decay. You didn't buy zero configuration. You bought a default good enough that you don't have to think. That 3e minus 4 from the very first line of this video is the limitation, wearing a friendly face. Adam won not because it's the most optimal, but because it's stable enough to become the default button for millions of people. Sometimes the winner isn't the most refined tool, but the most trustworthy one when nobody wants to tune by hand. Here's the whole family in a single sentence. Divide the stride by an estimate of the gradient size in that direction, separately for each parameter, then add inertia. AdaGrad RMSProp Adam. Every one of them is that sentence. The only thing that changes between them is how much of the past they choose to remember. That's the shock absorber our hiker has worn the entire video. One per direction, tightening on walls that have been steep, loosening on the flat. Now let's pay off the crack from the hook. Remember the promise from the first minute, that the exact trick which rescued AdaGrad is what quietly breaks Adam. Here it is, in full. AdaGrad's memory never forgot, so it froze. RMSProp taught it to forget, and that cured the freezing. But forgetting is also why Adam can fail to converge. From Reddy and colleagues in 2018. A rare but important gradient gets averaged away before it can steer. The fix, AdaGrad, simply tells Adam to never forget the biggest bump it has seen. The whole arc is one idea, slowly learning how much of its own past to keep. The honest paradox. Adaptive methods are both the foundation of modern deep learning and carry limits that sometimes send people back to plain old SGD, slower, but it often lands in a flatter, better generalizing spot. There's no absolute winner, only tools that fit their terrain. So what comes after Adam? 3 frontiers. Learning rate schedules. Changing alpha over time instead of trusting the optimizer alone. Second-order methods that read the curvature directly, like shampoo, and new generation optimizers built by search or by rethinking momentum itself, like Lion and Muon. The question the whole field is still chasing. Is there an optimizer as fast as Adam that generalizes like SGD? Do one thing before next time. Run the same tiny network with SGD, RMSProp, and Adam on a 2D ravine and watch the 3 trajectories. Then look back at the line we opened with. Optimizer equals Adam W, with the model's parameters and a learning rate of 3e-4. You now know every symbol hiding behind it. Next episode, learning rate schedules. Why the best training runs don't keep alpha fixed at all.